Hello everyone, I would like to start by wishing you all a good health and happiness. I am Bhavana Sitaphale, registration number 20 MSP 0035. In this video, I would like to talk about classical statistics, also popularly known as Maxwell-Boltzmann statistics. We would try to understand the derivation, which would in turn lead us to an equation which would give us the probability of a particle of being at a certain energy level. So let's start.
Consider a system with n number of particles, and these particles are identical but distinguishable. And let's say that these particles do not interact with each other. Let us keep the volume of the system fixed. So suppose V is the volume of the system. That remains constant. Capital U is the total energy of the system, or also we can say that total energy that is available within the system. So considering this few constraints, now we can move to Maxwell-Boltzmann statistics, this derivation. So as we have considered a system with large number of particles, so there is certain distribution within the system. So what do I exactly mean by the word distribution? So consider that D is E1, E2, E3, E4. These are the energy levels that are available within the system. So how many number of particles are there present in E1, how many of them are present in E2, how many are there in E3 and E4. So this is what we call by distribution. So by distribution, we actually intend to find the number of particles present in each energy level. And this can give us a lot of information about the system and can also help us derive certain quantities like the velocity distribution and much more. So let us move to the actual derivation. So let out of n number of particles, let n1, n2, ni number of particles be present in E1, E2, ei energy levels, which have G1, G2, Gi quantum states respectively. So now the question is, in how many ways, how many ways in which the group of particles from chosen from the total number of particles like n1, n2, ni will be chosen from this number of particles. What are the ways in which these number will be chosen? That can be given us by the formula that we learned in probability theory, that W1 will be equals to n factorial upon n1 factorial, n2 factorial, ni factorial, which can also simply be written as n factorial upon pi I n I factorial. This pi is nothing but, as we write sigma for summation, this pi is used as a multiplier. And these ni number of particles will be distributed in this Gi number of quantum states in Gi ways, ni ways. So let's say W2 is equals to pi I Gi is ni. So the total number of ways in which this particles will be distributed in quantum states will be given as W1 into W2, which is equals to n factorial upon pi I ni factorial into pi I Gi raise ni factorial. Now we can see that this is a little bit complicated equation, so we need to simplify it. So we were up to this equation, and by W we intend to find the maximum value of W, which will result in the most probable distribution value. So as we all know, taking differentiation on both the sides will give us the maximum value of W. So let's do that. Differentiating on both sides. D ln of W. So differentiating with respect to n. So we can see this n is nothing but the total number of particles which will remain constant. So this quantity comes 0. So we are left with minus sigma. This will give us d ni ln of ni by gi plus ni into dni by ni. This gets cancelled. So we are left with summation dni ln of ni by gi minus summation I d ni. So again, summation of I is, we know this term will lead us to the total number of particles, and differentiating it will again, which is constant, will give us 0. See, we are just left with this term and the most probable distribution. So if this is maximum, so we know that this term should be equal to 0. Therefore sigma I d and I ln of ni by gi should be equal to 0. Let us say this as equation 1 for further considerations. Our system is in the state of equilibrium, so the number of particles stayed constant and also the total energy is constant, like energy is conserved. So we can say that sigma I d of ni, which will be total number of particles, is constant, so it will be 0, and also total energy remains constant. So ei d ni will be equals to 0. Since let's just name this equation 2, let us name this equation 3. Now let's multiply equation 2 by alpha and 3 by beta, and then add it with equation 1. We will get sigma I d ni ln ni by gi plus alpha d ni plus ei d n, and this all is equals to 0. Now taking dni ln of ni by gi plus alpha plus, I'm sorry I did not add beta over here, multiply beta over here, so ei beta dni, so ei beta, this whole to dni, this also will come summation since sigma I, this will be equal to 0. Now this equation will only satisfy when all the ni, the group of particles like ni, are linearly independent, like this equation should only be satisfied when sigma I ln of ni gi plus alpha plus beta is equal. Using this equation, we are finally ready to derive Maxwell-Boltzmann distribution function. So using some mathematical tools, this will be the function where ni divided by gi will give us 1 upon e alpha plus beta ei. So this is nothing but Maxwell-Boltzmann distribution function. Thank you.